Good morning. Welcome to the oral session BC for online presentations. My name is Pedro Partal from the University of Huelva in Spain, and will be the chairman of this session. I will present all your presentations, and we can start with the first one. A dynamic balance leveraging HVDC and the cumulative method in power grid stability, presented by Aaron Weidinger from the Budapest University of Technology and Economics. When you are ready, you can start.
Yes, good afternoon. Can you hear me?
Yes.
Okay,
yes, we hear you.
Okay, then I will need just half a minute to share my presentation. Can you see the presentation?
Yes, you can start when you're ready.
Perfect, thank you. So, hello everyone, and thank you for joining me today. My name is Aaron Weidinger from the Department of Electric Power Engineering at Budapest University of Technology and Economics. Today I will be presenting our research titled Dynamic Balance, Leveraging HVDC and the Kuramoto Method in Power Grid Stability. This work explores how HVDC transmission systems and the Kuramoto model can be combined to understand and improve power system stability. Let me start with a brief overview of the agenda. At first, I will start by discussing current challenges in system stability, then examine how HVDC technology can support stability through grid segmentation. After that, I will introduce our modeling approach using the second order Kuramoto model, how we incorporated HVDC behavior, and finally, we will go through the simulation scenarios and our findings. So, power system stability defines the secure operating boundaries of the entire power grid. It determines how the system reacts to disturbances such as faults or line outages. In the recent years, the rise of inverter-based generation has significantly changed grid dynamics. We are seeing lower system inertia, more volatile frequency and voltage behavior, and also changing stability timescales. Traditional stability types like frequency, voltage, and rotor angle stability are still crucial, but they are now much more interconnected. Stability is no longer just a property of rotating machines. It's increasingly shaped by converter control softwares. This shift has introduced whole new forms of instability. As renewable penetration increases, the trade-offs between flexibility and stability margin becomes more pronounced. And this underscores the growing importance of adaptive controls and real-time monitoring. One promising path toward improved stability is the use of technologies that offer controllable power flow. Among these technologies, HVDC systems are particularly relevant, although they are often complemented by effects devices on the AC side. HVDC lines contribute to stability in multiple ways. They can control the direction and magnitude of power flow with high precision. They also allow asynchronous interconnection between regions if needed, and they can act as active stabilizing elements through these properties. Importantly, this control comes without compromising network connectivity. Unlike traditional AC lines, they also introduce lower transmission losses, as it can be seen on the picture. Another strategic advantage of HVDC lines is their use as network isolators. By strategically placing HVDC links, large power systems can be divided into several subsystems. Uh, this approach reduces the risk of cascading failures and widespread blackouts, as disturbances can be contained within one within one segment, um, without spreading across the entire grid. Unlike reducing connectivity, which compromises system performance, this segmentation maintains high interconnectivity while also boosting resilience. Simulations by researchers show that HVDC isolators, when designed carefully, can block failure propagation even in highly connected grids. The diagram on this slide shows how AC grids can be segmented using DC links while still enabling power exchange. And to explore these ideas safely and systematically, we need models, of course. And our goal was to analyze system behavior under different configurations without relying on real world measurements, which are often also impractical or risky. For this modeling, we used the second order Kuramoto model, which is a well known framework in nonlinear dynamics. And this model captures the behavior of interconnected oscillators, in our case, grid nodes, which are generators and loads. And it describes how their phases and frequencies evolve over time. Um, each oscillator has its own natural frequency, omega 0, a damping term alpha, representing inertia, and the coupling strength K, and that describes its interactions with neighbors based on weighted neighborhood matrix A, and the number of connections N. Together with the oscillator's phase angle theta, these components determine the rate of change of its frequency over time, reflecting the dynamic balance within the network. For the model, we used INSO-E's 2016 grid topology data to construct a large-scale European test system. Although the production and consumption data were missing from the database, we assigned zero-centered Gaussian distributed frequencies to the nodes to simulate heterogeneity. It is important to note here that this model is, of course, dimensionless this way. Integrating HVDC behavior into the Kuramoto model is not easy. AC and DC systems operate under very different principles. So we had to decide what aspects of HVDC do we want to focus on. One option was to model fixed power transfer, which is predictable and constant. And alternatively, more advanced representations could simulate adaptive control, for example, regulating power based on frequency deviations or phase angle differences. But these two would require a deeper modification of the equation. So we choose a middle ground approach, modeling HVDC lines as direct power sources and sinks at the end nodes of the given edges. And this allowed us to reflect the nature of HVDC systems while also keeping the implementation feasible. We implemented these links as fixed power flowing in and out from the given nodes, and treated their AC counterparts as zero-weight edges. Our simulations began by modeling all currently operational HVDC lines in Europe. Then we moved onto a Hungarian test scenario where extra HVDC links have been added based on literature and real events, such as the 2021 Balkan incident. And these lines can also be seen on the first picture in red color. Each simulation started from a fully synchronized state and ran for 300 time steps, which allowed the system to reach steady state. We ran 100 trials for each case to eliminate the effects of randomness and ensure robust averages. The first graph shows the Kuramoto order parameter R. It measures phase synchronization ranging from 0 to 1, with 1 meaning full synchronization. The x-axis is the coupling strength K, which is essentially the maximum transmissible power between nodes, which spans from 500 to 20,000 in this case. And here the black color represents the baseline case where HVDC lines are not specially modeled, they are neglected. The red line includes existing HVDC lines, and blue adds the Hungarian imaginary scenario. We saw only modest improvements at some points, mainly for small k values, but importantly, HVDC does not degrade synchronization too much. This shows that adding DC links doesn't destabilize the system, which is at least a good starting point. The second figure shows the lambda frequency parameter, which measures how closely the average frequency at each node follows the system-wide average. And again, K is on the x-axis. The trends are similar here as well. HVDC presents doesn't drastically change synchronization, but slightly ruins frequency cohesion with somewhat bigger frequency deviations. Um, and this shows us a drawback of the non-adaptive modeling approach that we were using. In our final test, we simulated cascading failures. After reaching steady state, we randomly removed the power line to simulate a fault. And if then surrounding lines exceeded a power threshold, then they were removed as well, simulating a domino effects, so to say. And after that, we recorded the average number of lines that failed as a result, shown here against the coupling strength. And unfortunately, there was no clear improvement. In some cases, adding HVDC even led to larger cascades, likely due to rerouting effects and practically disturbing the graph itself. To summarize, HVDC links didn't significantly improve global synchronization or reduce cascade size with this modeling approach compared to the reference case. However, HVDC links did not notably worsen synchronization, but they also did not significantly reduce the average cascade size. Interestingly, the Scandinavian region consistently showed the weakest synchronization, which in fact also has the most HVDC links, which could be an explanation to slightly weaker synchronization. Going forward, we plan to test adaptive HVDC control strategies in order to step outside of the limitations of this modeling approach. For example, making the power transfer responsive to local frequency or angle deviations. And this may offer the improvements we hope to observe, but will require deeper modifications in the model. And thank you very much for your attention.
Thank you very much for your presentation. We have 1 minute for a question in the room. Any question? Okay, I have a question. I think this is a preliminary study. Do you think, I would like to know that if this theoretical result could be easily translated to practical engineering context in the end?
Excellent. Thank you for the question. I think it would be hard to implement it to reality at first because of the dimensionless approach of the model. But it is great to see the big picture, so to say, for the whole European grid. And also for practical use, we would also need to improve the database and collect more data.
Okay. We have no question here. Thank you for your presentation.
Thank you very much.
We go to the next talk. It's entitled Assessing Deep Reinforcement Learning Control in Permanent Magnet-Assisted Synchronous Reluctance Machines, that will be presented by Cristina Martín from the University of Sevilla. When you are ready, you can start.
Hello, thank you. I will share the presentation. So can you see the presentation?
Yes, we are seeing your presentation. Maybe you should click on presenting. We are seeing your PowerPoint.
Okay, perfect. I will start first. So good afternoon, everyone. My name is Cristina Martín. I'm with the Department of Electrical Engineering in the University of Seville. And I'm going to present the work entitled Assessing Deep Reinforcement Learning Control of Permanent Magnet-Assisted Synchronous Reluctance Machines. So let me start by explaining why deep reinforcement learning could be a suitable strategy for controlling this kind of motors. These machines are becoming popular as an alternative to traditional permanent magnet synchronous motors due to some advantages such as high efficiency, reliability, and mainly reduced cost thanks to the lower reliance on rare earth magnets. The problem is that they present significant magnetic nonlinearities, such as saturation or cross-saturation effects, which complicate their control. In this regard, traditional predictive controllers, such as finite control set MPC, rely on simplified linear model of the system that do not capture this nonlinear behavior. Since the predictive controller require an accurate model of the system to obtain a good performance, this simplification can lead to control degradation. Other solutions involve high-dimensional flux maps, as the ones presented in that figure, or complex analytical models that increase the computational cost. In contrast, deep reinforcement learning offers a model-free alternative. It learns control strategies by directly interacting with the system, adapting to complex nonlinear behaviors without requiring an explicit model. And that is why we think this could be a good solution for that problem. Our main contribution is a model-free DRL control algorithm designed specifically for this kind of drives, has an alternative to the traditional finite control cell MPC. We validate its performance through simulation and compare it against the predictive control scheme in terms of current control and harmonic distortion mainly. Additionally, we evaluated the robustness of the controller by injecting measurement errors, and also we tested the dynamic performance. We will see the results later.
Sorry, Cristina.
Tell me.
Sorry to stop you. I think we are not seeing your presentation. We are seeing the first slide of your presentation.
Only the one.
Yeah, only the one. That's the reason why at the beginning I told you to start with the presentation. So
Okay,
I don't know if you are using two screens or I don't know why.
I don't know why. Maybe.
Yeah, we are seeing your mouse. And
yeah, I will try to share the.
If you allow us to assist you, you may have to share the screen where the presentation is displayed.
Yeah,
you are sharing the,
yeah, but I only one screen, so that is why I don't understand. But I will try again. Can you see now the second?
now we are
slide?
seeing your slide. Thank you.
And the next one?
And the next one, yes.
The problem is that you have to share the complete window, not the document. That is the mistake.
Okay, you can continue.
Sorry for the. Okay, so after I explain the contribution, you can see there here that basically is this DRL-based control algorithm. I will explain the system that will be used as a case example. It is a three-phase machine fed by a two-level voltage source converter. And its dynamics is modeled in the DQ reference frame, since it is the common practice for control purpose. And well, here are the main equations, the stator voltages and the torque. The challenge is to model the nonlinear behavior relationship between fluxes and currents, as commented before. For the predictive controller, we use a linearized model of the system with constant inductances. But for the DRL agent, we train it with a nonlinear model of the machine. Basically, we use the flux maps obtained by finite element analysis. The proposal control is schematically represented in the figure. Replace the current loop in a conventional FCS MPC with a DRL agent. So there is an external control loop that regulates the rotor speed and provides the optimal DQ current references. Then the agent receives an observation of the system state composed by the current references, the measured currents, and the rotor angle. And based on that information, it selects one of the 8 possible switching states of the converter that constitutes the action, the control action. Previously, the agent has to be trained to know which action leads to the minimum current tracking error, which is the goal of the current controller. To do that, the DRL agent is based on a double deep Q network. It uses 2 neural networks, the online one, which selects the action, and the target network, which helps the training process by estimating the Q values. During the training process, the agent interacts with an emulated drive that is represented in the figure with the switch that changes to the T position. And at each step, it receives an observation of the system, selects an action using an epsilon greedy policy. That means that with probability epsilon, the agent chooses a random action to explore. Otherwise, it exploits the best known action based on the Q values. After that, the agent receives a reward that quantifies the quality of the decision. And in this case, the reward penalizes the current tracking error using a logarithmic function as it is represented in the equation in the slide. And finally, the agent updates its Q values using the Bellman equation with the goal of reducing the difference between the predicted and actual cumulative rewards. This process is repeated iteratively until convergence to an optimal control policy. Okay, so the results we obtain by simulations are this one. First, we analyze the steady state performance over different operational points. This is an example for 150 radians per second of speed and a constant low torque. On the left, you can see the rotor speed and the stator currents with their reference values. It is obvious that the controller can effectively regulate the system. On the right, you can see the phase currents that shows an adequate sinusoidal shape. After that, we compare the proposal with the conventional predictive control at different operational points to do a better comparison for sure. And we use two figures of merits for this comparison, the root mean square error of the DQ currents and the total harmonic distortion in the phase currents. The results are resumed in this table, and in all cases, the proposal outperforms the traditional controller. So it improves the current raking performance and also reduces the harmonic distortion in the currents. The reason is simple. The DRL agent captures the nonlinear behavior of the machine, and the simplified model used by the predictive controller does not do that. We also tested the robustness of the controller to measurement error up to 3%. In this case, the root mean square error of the currents is used as a representative figure of merit, and the results show that a moderate performance degradation appears with increasing error, but maintaining an effective system regulation. So we can say that the controller is robust to this noise in the measurement. Finally, we also tested the transient performance, the dynamic performance, with two tests. A speed variation from 100 to 200 radians per second, with the result in the left plot, and a low torque step from 10 to 20 Newton meter in the right plot. In both cases, we can see that the controller demonstrate an adequate transient performance. In conclusion, we can say that the proposed controller provides a robust, adaptive, and efficient alternative to the classical FCS MPC for this type of drives. And the reason is that it learns from nonlinear dynamics without requiring a precise model. Also, it maintains a good accuracy under sensor noise and dynamic conditions. Computationally speaking, although the training process can be intensive, the trained agent operates efficiently in real time, so an experimental deployment could be possible. As future work, we will focus for sure on the experimental validation and improving the learning process too. So thank you for your attention.
Thank you very much. You're finishing time. Is someone there to
Have a question?
Have a question?
Okay, I think you have told something about this, but I would like to ask you, is the model able to consider transient events or faults, for instance, sudden load changes or voltage dips? Have you tested this?
Faults in the machine.
Yes. Faults.
No, we didn't test that. It could be interesting. Maybe faults in the machine could be difficult. Well, in practice, I mean, in experimental testing. But maybe an open phase in the voltage converter could be tested easily. It could be a good test, but we didn't do it. This is our first contribution in this topic.
Great. Okay, thank you very much for your interesting presentation. We will continue with the third one. Experimental determination of the temperature coefficient of resistance of ACRSR conductors using a radial conduction model. Presented by Ankit Soni from la Universidad de Politécnica de Cataluña. When you are ready, you can start.
Sure, Professor. Sorry, 2 minutes. Yeah. So can you see my screen?
Yes, we are seeing your first slide. Click on
change?
presentation to see you.
Okay. Can you see the changes? I'm changing the slides. Can you see it?
No, we are not seeing the change the slide. We are
Okay.
seeing the first slide. So
Sure.
please share your screen.
Yeah, sure. Okay. So, Professor, now I think it is visible.
Yes, now we are seeing your
Okay. Okay. So, first of all, thank you so much for giving me the time for presenting my work at ICREP. I'm Ankit Soni. I'm from Sicame, Spain, and also from the University Politècnica de Catalunya, Barcelona. So, my topic is experimental determination of the temperature coefficient of resistance of ACSR conductors using a radial conductor model. So, uh, we all know that the demand for power transmission is rising. So, because of this thing, it is very much challenging to use the existing infrastructure efficiently. Otherwise, we need to spend more money for creating the new infrastructure for meeting the more power transmission demands. So for that purpose, the DLR approach has been used. The dynamic line rating approach has been used, which is basically uses the weather conditions as well, so that we can efficiently use the existing infrastructure and existing conductors. Uh, for example, very much efficiently based on the real-time weather conditions. For example, if the weather is cold, then we can introduce more and more power and more current into the transmission lines. And if the weather is hot, then we need to reduce down the current and the power. Because for the ACSR conductors and for other conductors, we do have a thermal capacity limit. For example, for the ACSR conductor, it's 80 degrees centigrade. So the temperature of the conductor should not exceed 80 degrees centigrade. But using that DLR approach, we normally consider only the surface temperature. Uh, but in reality, the temperature changes from the core to the surface. So for example, at the surface, the temperature is always less as compared to the core. So if we are considering only the surface temperature as the average temperature of the whole conductor, that might create the some error for predicting for our DLR prediction, for the dynamic line reading prediction. So what I have tried to do is I have tried to create the model and doing some changes into the DLR model, so that we can also just like see what is the actual average temperature of the conductor. So the objective is propose a method to accurately predict resistive losses, because that prediction of the resistance, you uh, through the correctly measuring the temperature, also affects the resistive losses. So which is very much important factor for the dynamic line rating models. So I've used these three types of the conductors, the ACSR conductors. So there is for the ACSR conductors, we always have the steel core to support the cable, and we always have like the one layer, two layer, or three layer of the aluminum conductors. So these are the conductors that I have used it for my experiments, and these are all the specifications. So for these conductors, the AC resistance not only depends on the temperature, but it also depends on the current level, which is not like a simple formula for determining the AC resistance of these conductors. So because the why it is dependent on the on the level of the current as well, because we are having the steel core like this in all the three ACSR conductors, which creates the axial magnetic flux, which actually causes the extra AC resistance. So yeah, so this is the theoretical background, uh, how I have used the model. So as you can see it here, it is like the normal conductor. So I've used this particular model for improving my DLR model. So it is like the P stored, which is actually causing the increment of the temperature of the conductor. P internal, which is basically because of the resistive losses flowing the current inside of the conductor, and the resistive losses. There is again like the P solar, which is actually increasing the heat because of the solar radiation, and the convection part, convection cooling is there, and the radiative cooling is there. So in the normal situation, we only normally consider only the surface temperature, but while using this particular model, I have tried to calculate the average temperature. So here there are different sections starting from the surface to the core. This particular part is for the aluminium. So uh, I have used this particular model for the P stored, means increasing the temperature. P generated is basically because of the current, I square R. P input is because of the conduction conduction part, which is coming from the higher temperature to the lower temperature side, which is actually like the convection part, which is coming conduction power, which is coming from the core to the surface, and the P output, which is from this segment, which is just like going out. So I've used this particular model to get the temperature at the core, and as well as for the average. Okay, so this particular experimental model, so as we can see it here, this is the high current transformer, and this is the low impedance circular loop. I've used my conductors like this. This is like the Rogowski coil for measuring the current, and I have used this data acquisition system for getting the voltage and current. And also I've used the three types of the thermocouples here in these parts for getting the surface temperature. So these are the instruments I've used: current, voltage, data acquisition system, temperature, T types of the T type thermocouples, because it has like higher accuracy, and uh, it's very fast thermocouple duct. And I've used the Python code for analyzing, for accessing the data from the data acquisition system and from the thermocouples. And for MATLAB, I've used it for the models. So after putting the models, we can see it here in the single layer conductor. Uh, the experimental surface temperature is this, whereas the simulation core, the core temperature that we have got it through the model, is like there is around 1 to 2 degrees of the differences. And between the simulation average, between the average temperature of the conductor and the surface temperature, it's around 1.5 to 2, it's around 1 to 1.5 degrees centigrade of the differences. Because of these differences, there is always a change into the thermal coefficient of the resistance, which is very much important to predict the actual resistance at different temperature level and at different current levels. So we are seeing it here, it's always decreasing from 4.62 to 4.52. It is decreasing. uh, if we will talk about the two layer conductor, there is again the temperature differences around 2 degrees, approximately 1 to 2 degrees from the surface to the core. And because of that differences, The alpha average means the average thermal coefficient of resistance that we have got it through the model, and this is through the experimental value. So there is always the differences, and this alpha average is always lesser than the alpha surface from the experimental values. For three-layer ACSR conductor, the difference is much more visible. We can see it like the difference of around 4 to 5 degrees, and the difference from the average temperature to the surface temperature. Average temperature means like the actual temperature of the conductor that we can consider it. So it is the difference is around 4 to 5 degrees, and because of that difference, we can see the changes into the thermal coefficient of resistance alpha. So this is the summary. So for single layer conductor, at different level of the currents, the thermal coefficient of resistance was different, uh, starting from 4.62 to 5.09, and their corresponding alpha average, which is always lower than that of their experimental values. Also, it is same for the two layer conductor, but for the single layer conductor and for three layer conductors, we can see the changes of the alpha with different level of the current. But for the two layer conductor, it is always same with different current levels. So because there is another finding behind it, because whenever we use two layer of the conductor with the steel core, then if the number of the layers are even, then they cancel out each other's magnetic flux effect, and because of that thing, we have got the AC resistance stable, not changing with the current level. But because if if we will use the odd number of the layers into the conductors, we will always have the differences into the alpha, and also the level of the resistance at different current levels are different, because the one extra layer in the in the odd layer of the conductors, it always creates the extra magnetic flux, so which causes the extra AC resistance because of the magnetic flux effect. So so this is the conclusion. Develop the thermal model to accurately estimate average radial temperature. So the model that we have done is more accurate for getting the more accurate value of the resistance, and subsequently having the more accurate dynamic line rating model. Uh, so the current level significantly affects its resistance in alpha in single and three layer conductors that I have already explained it, but not in two layers of the conductors because of the even and odd layer number of the layers. And apart from that, the radial temperature gradients lead to the lower average alpha than the alpha surface values. And the last one is because we have improved the model, so model improves accuracy of DLR applications and supports safer, more efficient power transmission. Okay, these are the references. Thank you so much, and please feel free to ask the question. Yes.
Thank you, Ankit, for your interesting presentation. I have a curiosity.
Yeah.
You have understood your experimental setup.
Yeah.
You test your material, your system, and
Yeah.
the force heat for convection heat transfer for convection.
Yeah.
Because you are using fans. Have you tried to study, or have you seen the effect of, for instance, when you have free convection, or
Uh,
even when you
yeah.
have solar irradiation?
Yes, Professor. Actually, the thing is, for this particular experiment, actually, I'm doing so many different experiments. For this particular experiments, I have not used the fans, so it is without the fans and without the solar radiation. Uh, Hello, Professor.
Sorry, any
Yeah.
question? No? Okay, thank you very much for your presentation.
Thank you
We
so much.
continue with the next one.
Sure. Thank you so much for the time.
Next presentation is entitled J-based
optimization of a surface-mounted permanent magnet synchronous motor, presented by Pedro Cruz Romero from the University of Huelva. If you're ready, you can start with the presentation. Thank you very much.
Yes, thank you for your introduction. Can you see the presentation?
We see your presentation, but the noise is not good. Sorry, we can hear you very well.
It's okay now?
A little bit. Try to speak, and we'll see.
Okay. The paper deals with the optimization of a surface-mounted permanent magnet synchronous motor through genetic algorithm. All the authors belong to the Department of Electrical Engineering from the University of Sevilla, and the project has been funded by the Ministry of Science, Innovation and Universities and co-founded by the European Union. Why do we study this kind of motors? Because they are widely used in many applications due to the high torque density, high efficiency, fast dynamic performance, and simple geometry and simple manufacturing, as can be seen in the figure, where the stator is similar to an induction motor stator, and the rotor is a simple rotor built with an iron core and a surface-mounted permanent magnet. In general, this kind of motor can be built in a simple way. The research objectives of the project are, on one hand, a single objective result that is minimize the current, the quadrant axis current, and another double objective that is minimize not only the current but also the motor weight, maintaining 66 Newton meters of torque in all the cases, and using the genetic algorithm for optimization. The analytical model has been taken from references 4 and 5 that belong to the Gianmario Pellegrino team from the Politecnico di Torino. And we can see the expression of the torque that is only related with the magnet torque, not with the reluctant torque. The reluctance torque is 0 because the motor is symmetric. Another important parameter is the torque constant. That is the inverse, the torque constant. If the torque is constant, the denominator is the only variable. So the torque constant optimization is similar to the current optimization. In the torque constant, we have several geometrical parameters like the rotor stator inner radius, the radius, the stator inner radius, sorry, the length of the stack, the number of turns per coil, per phase, the coefficient of winding, and the fundamental component amplitude of the density flux. The stator inner radius is in turn a function of the X parameter that is defined as it is here. The X parameter is a non-dimensional parameter and can be defined the upper and lower bounds. The fundamental component amplitude of the magnetic field is obtained through a Fourier transform, where it is related with the magnetic field distribution and the angle, the pole span angle that we defined previously in the figure. The pole span angle is this one. So with the Pauli span angle and the distribution of magnetic field, we obtain the amplitude of the fundamental component of the air gap field. And the distribution of magnetic field in the air gap is also a function of the remanence of the magnetization curve, and also of another parameter B that is an dimensional parameter, and is defined as the thickness of the magnet divided by the air gap. We have also calculated the motor mass of the motor mass, and composed of 4 terms: the stator mass, the rotor mass, the conductor mass, and the permanent magnet mass. All these weights or masses are related with the volume of each part that is not presented in the presentation, but can be seen in the full paper. We have started with a reference machine specifications that belong to a typical machine, not optimized, and where we show here the 8 parameters we have used in the genetic algorithm. The parameters are more or less in the middle part of the range of its value, and the results of the analysis with these the analytic formulation with these values are the torque of 66 Newton meters, the current with 27.7 amps, and the weight with 18.5 kilograms. So the idea is trying to improve the results of this reference machine with the application of the genetic algorithm. So the genetic algorithm is use mu plus, maybe we can see minus, but it's plus. Mu plus lambda genetic algorithm that we have used in 2 steps. In the first step, we create an offspring population lambda generated from parent population mu. And in the second step, we select from the combined population lambda plus mu. We obtain the next generation. The individual representation of is the chromosome of the genetic algorithm, is composed of these elements that are the same than the previous seen before. These elements, these parameters are the same than these. And these parameters have a variable range defined, limited, fixed, between a lower bound and an upper bound that are in this table. So we can see that, for example, X ranges between 0.5 and 0.7 typically, and B between 3 and 6. For the obtention of the lambda population, we use 2 genetic operators, mutation and crossover. The mutation is the random parameter change with feasible bounds, and the crossover is the combination of the genetic material from 2 parent individuals. With mutation and crossover that are random functions, we obtain the lambda offspring from the mu parents. The simulation parameters are for hence the mu population of 1,000 individuals for the single objective and multi-objective, the lambda population also for the single objective and multi-objective, the number of generations, 100 for the single objective and 100 also for the multi-objective, the selection process to obtain the next generation that is different from single and multi-objective. The tournament is a typical method used in the single objective, and for the multi-objective, we have used the NSGA, that is the non-dominated sorting genetic algorithm that also typically used for double objective problems. The probabilities of crossover and the probability of mutation are for the single objective are a set of 4 values, and also a set of 4 values for the mutation, and they are combined in couples. For example, 0.5 with 0.5, 0.6 with 0.4, etc. And with these probabilities, we have obtained the best solution that is reached with the 0.5 and 0.5 probabilities. So these probabilities, these two probabilities have been extended to the multi-objective problem with also 0.5 and 0.5 probabilities. So the results of the genetic algorithm for the single objective optimization is to minimize the current required for 66 Newton meters torque, and to get an optimized current that is, after running the algorithm, is 15.20 amps. That means a 45 reduction with respect to the 27.7 amps that we obtained in the first motor. The motor weight is approximately 30 kilograms. That is a heavy value because the optimized current is in conflict with the optimized motor weight. The best solution for this best solution, the parameters are shown in the table, and in most of the cases, the parameters are in the upper bound of the range of the values. We have obtained other parameters, mainly related with the slot of the stator, like the area of the length of the slot, the H2 in the figure, and they are in general smaller than the reference machine. So the idea is obtaining a machine with a smaller size of slots. For the multi-objective optimization, we have to minimize the current and the weight, but they are conflicting objectives. We cannot minimize the current and also minimize the weight. So we don't have a single value, a single resultant value, but we have a Pareto front where it is a set of solutions that none of them are the best solution, but we have a set. In this figure, we have one point where the solutions of current and weight are quite satisfactory. In this point, the values of the parameters are here in this table, and most of them are in the upper bound of the range, with the exception of the stator outer radius that is in the lower bound. We have also obtained for the multi-objective optimization problem the size.
One more minute.
Okay. We have obtained also the size of the area and the length of the H2 parameter that are like in the single objective problem, they are lower, they are smaller than in the reference machine. As conclusions, we have implemented a genetic algorithm for the effective optimization of surface permanent magnet synchronous motor design. It is written in Python using deep library. The performance is quite significant for the single objective, the current reduction, with 45% of improvement. And for the multi-objective solution, the improvement is 28% for the current and 13% for the weight. Regarding the future work, we can include also the thermal analysis with the heat transfer from copper losses, and also we can add practical manufacturing limits, more additional practical manufacturing limits other than we have used now in the paper. And that's it.
Okay. Okay, thank you very much. We have no time for questions, so we need to continue with the second, no, last presentation, entitled Energy Management of Ground Generation Airborne Wind Energy System, that will be presented by Pablo Flores Martín from the Universidad Carlos III de Madrid.
Hi.
You are ready?
Hello. Yes, wait a second. Can you see my screen? Yes, I think.
Sorry, the quality is very poor. Because, no, it's improving a little bit.
Okay.
Yeah.
Is it? No, I'm just sharing my screen best I can.
Okay.
Okay. Well, good morning. My name is Pablo Flores Martín from the Department of Electrical Engineering at Universidad Carlos III de Madrid. And today I'll be presenting the first fully realized energy management system developed for ground generation airborne wind energy systems, or AWES for short. AWES is a revolutionary technology that captures energy from high altitude winds, which are typically stronger and more consistent than those near the ground. It achieves this by utilizing a tethered kite connected to a ground-based generator. It produces energy in a two-phase cycle. During the power phase, also called the reel out phase, the kite pulls on the tether as it unwinds from the drum, turning the generator and therefore generating electricity. To maximize pulling force, the kite flies in figures of 8, which increase its apparent wind speed and thus increase the lift generated by the kite, generating more power. Once the tether reaches its maximum length, the system enters the retrieval phase, also called the reel-in phase. In this phase, the generator switches roles and acts as a motor to reel the tether back in. This utilizes only a small fraction of the energy produced during the reel out, meaning that the net result is a positive energy that can be fed into the grid. But then the question arises, why choose this technology over conventional wind turbines? Well, AWES preserves only the essential components needed for wind power generation. It eliminates the need for the massive tower structure found in traditional wind turbine and instead transfers the aerodynamic function of the blade into a lightweight kite, moves the generator to the ground, and connects them both by a tether. By simply increasing the tether's length, the system can reach much higher altitudes than conventional wind turbine. At those altitudes, winds are stronger and more stable, leading to an increased power output. Because AWES uses fewer materials, the system becomes significantly cheaper and more compact for the same given power output. This makes it easier to transport and install, especially in remote or disaster-affected areas, where conventional wind turbines are difficult to deploy. However, AWES also comes with a major challenge, its power profile. To help illustrate this, I'd like to show a short animation. This animation will show here the kite path during flight, and here the power generated or consumed by the kite. At the beginning of the cycle, the kite stabilizes its position without reeling out, and no power generated yet. Then the reload phase begins, the tether starts unwinding, and the kite begins to generate power. You'll notice that the power output isn't constant. There are generation peaks during the straight segments and generation valleys when the kite turns. Once the tether reaches its maximum length, the system transitions into the reel-in phase. At this point, the kite moves out of the wind path to reduce resistance, and the generator acts as a motor to reel the tether back in. And during this phase, the motor consumes power. As you can see, the resulting power is cyclical, with alternating periods of high variable power generation followed by power consumption. This cannot be directly fed into the grid, therefore energy management must be done. To manage the AWS profile, the proposed energy management system uses a compact DC microgrid, ideal for lab testing and future field deployment. It has three main sections. First, the AC section, which includes the AWS generator and the grid connection. Second, the DC section with a battery and supercapacitor, both managed through individual DC-DC converters. And third, a braking resistor, also using its own DC-DC converter, which enables controlled energy dissipation in overvoltage scenarios. The hybrid battery supercapacitors energy storage system allows each element to do what it does best. The supercapacitor handles most of the AWS profile, absorbing and delivering rapid transients, while the battery focuses on maintaining both the supercapacitor voltage and the DC boost voltage at all times, keeping its own current low. The battery operates in high voltage side control, meaning that the DC boost voltage must be maintained at all times between 1 per unit and 1.06 per unit. If it goes above that limit, the battery absorbs power. If it falls below that limit, it delivers power. If it stays between, it stays idle. On the other hand, the supercapacitor operates in low voltage side control with a current limitation, allowing to adjust its power absorption or delivery continuously. Okay, so now let's look at how the supercapacitor smooths out the power profile to enable a constant power delivery to the grid. The top image shows a simplified version of the previously shown hour cycle. In green is the reel out, and in red is the reel in. And the image below illustrates how energy is distributed across the cycle. During the reel out, part of the energy generated goes directly to the grid, while the supercapacitor absorbs the rest of the power generation. And conversely, during the reel in, the supercapacitor, previously charged, now discharges to meet both the reel in demand and the grid demand. This behavior is illustrated in the following hour cycle. The top graph shows the DC boost voltage. The middle graph shows the power flows in the microgrid, the battery supercapacitor, electric machine connected to the AWS and the grid, and the bottom graph shows the supercapacitor voltage. As the cycle progresses, the supercapacitor tracks the AWS power profile offset by the constant power delivered to the grid. The boost voltage remains relatively stable with small oscillations, especially during the reel out, due to the time it takes the supercapacitor to adjust its power absorption. In the bottom graph, we see the supercapacitor charging during the reel out and discharging during the reel in. Since the supercapacitor has returned to exactly its initial voltage, we can conclude that this cycle has a net energy of 0. If every cycle had a net energy of 0, the supercapacitors could manage the AWS profile indefinitely. However, in practice, that is not always the case. If the net energy of a cycle is slightly negative, the supercapacitor voltage tends to decrease, and if it's slightly positive, it tends to increase. Over time, these trends can make the supercapacitor voltage reach its upper or lower limits, at which point it can no longer manage the power transients of the hour's profile. And to prevent this, the battery must step in advance, either absorbing or supplying energy as needed to keep the supercapacitor voltage within safe bounds so it can manage the hour's profile. To know the amount of energy the battery must either absorb or supply, the proposed energy management system uses a combination of predictive and feedback control. The predictive term estimates the net energy of the next cycle based on the wind conditions at the time. And the feedback control term compares the actual energy of the supercapacitor with its reference, calculated from the voltage deviation with 1 per unit, which is its reference voltage. Adding both terms gives the total energy the battery should compensate, should either absorb, which is positive, or supply, negative, in the next cycle. However, if this energy is sufficiently small, the battery can stay idle. It's only involved when the required compensation is large. In that case, we calculate the constant power the battery needs to either absorb or supply in the following cycle. Now, remember that we said that the battery operates based on voltage thresholds at the DC boost side. Therefore, we need to force a small voltage shift in order to prompt the battery to activate. We do this simply by applying an offset to the supercapacitor's power equation. This alters the power balance on the high voltage side, triggering the battery to respond. This will be easier to understand with a visual example. These three graphs, same as before, show the boost voltage, the power flows, and the supercapacitor voltage in 3-hour cycles. The first cycle is a standard case, same as before. However, the supercapacitor ends the cycle at a high voltage. To correct this, an offset is applied to the supercapacitor's power reference during the second cycle, as it can clearly be seen here. This causes a gradual rise of the DC boost voltage, and once the boost voltage exceeds the battery activation threshold, the battery begins to absorb power to bring the voltage back down. This process repeats until the end of the cycle, where the supercapacitor, because of the offset, reaches its reference voltage. Therefore, during the third cycle, no battery intervention is needed. This proposed energy management system has proven effective in simulation across multiple hour cycles. It maintains a stable power supply to the grid, the green line, while the supercapacitors absorb all power transient, and the DC battery ensures that both the supercapacitor voltage and the DC boost voltage stay within safe limits. Additionally, the proposed energy management system was successfully deployed on the physical microgrid shown before, where it managed to regulate the reload phase of an hour cycle, while keeping the DC boost voltage within the activation thresholds of the battery, allowing the battery to remain completely idle throughout the full cycle. In summary, this work presents the first fully implemented energy management system tailored for ground generation airborne wind energy systems. It has proven in simulation to be able to deliver a stable power supply to the grid, manage the supercapacitor's voltages, and maintained the battery idle during most cycles, therefore preserving its life. And it also has proven in physical testing that the supercapacitors can effectively manage all power transients while maintaining the boost voltage stability and therefore keeping the battery idle. These results demonstrate the feasibility of reliable energy control in hours-based microgrids, a key step toward practical high-altitude wind energy integration. Thank you very much for your attention.
Thank you very much for your presentation. I have one question about your result. Do you think that communication delays could affect real-time control performance?
Yes, and they actually did when, for example, in the simulation. Let me show you. In the simulation, the delay time between the activation of the reading of the power delivered by the OS and the power absorption or delivery by the supercapacitor was smaller than later during the actual testing. In the simulation, it was set to 50 milliseconds, and it was shown in the actual testing that it was closer to 100 milliseconds, and this caused the boost voltage oscillations to be higher than in simulation, although they were kept within the activation thresholds of the battery at all times. Sorry, you're muted. I cannot. So,
Sorry. Thank you very much for your presentation. We have no more time for questions, and we need to close to finish this session. Thank you very much for all the presenting authors and for the very interesting result that you have chosen. Thank you very much.
thank you.